Hello and welcome to this small voiceover on the exercise text for report number 2, which you can see up here. And the topic for this report will be the damping of our offshore wind turbine. So the 4 main pillars are initially a modal analysis, but it is not for the full system. It's a reduced order system. That means we're going to apply some kind of system reduction procedure, and we're going to use the dynamic static split of the degrees of freedom into 2 parts, and we'll only analyze the dynamic part dynamically. Then we'll have a second part that concerns damping, and first we introduce a pure viscous damper acting on the structure, and the idea is, of course, what is the optimal viscous parameter for this device to actually introduce maximum damping into our structure. And the next approach, we will then introduce a so-called TMD, a tuned mass damper. That is a spring in parallel with a dashpot supporting a supplemental mass, and then we have our structure over here that vibrates. So in this case, the damper suddenly becomes a resonant damper because we have an interplay resonance. We have an interplay between K and M, and that gives us a natural frequency, basically as K divided by M. So this additional damper natural frequency then maximizes the energy dissipation in the dashpot here, and thereby a TMD is often more efficient than a viscous damper. But it all depends on the loading and the vibration modes and where you can apply the damper. Our problem is again this jacket-founded offshore wind turbine, and my dear friends at Tilsted also provided the geometry for this report, and it's the same as for report number 1. So the initial text concerning the offshore wind turbine, which we'll also see in the next slide, is basically the same as we had in report number 1. I've added a little bit here at the bottom, augmented it a little bit to describing the X array we have here representing the nodes, the topology, and the T array, so maybe it becomes a little bit more informative. As you can see on the top right figure, we only now consider a distributed loading, so no gust loading in this exercise. So it's only the vortex-induced loading that is considered. So we have a distribution of our load. It's evenly distributed, like we had in report number 1, and there's some kind of temporal intensity describing the harmonics of this loading. The structure itself is again defined, and it's the same table as we had in report number 1, so there's no need to extensively review this table if you're already acquainted with it from report number 1. So let's go back to the loading. So as you can see, there's no gust loading applied here, it's only harmonic loading. And this loading is, as in report number 1, described by a sine function, and PV is again these 500 Newton per meters. What is new is that we are going to change omega V. In report number 1, omega V was 9.0 radians per second. In report number 2, we have 2 cases. First case, then omega V will be equal to omega 1. That's the first mode frequency. And isn't that quite close to 2.0 radians per second? Look it up, do an eigenvalue problem analysis, and find omega V. So that's the first case, referred to as number 1 here in this item section down here. So with this mode, we would like to excite the first vibration node of the structure. But we also consider load case number 2. It has the same intensity, it's the same sine function. The only thing that changes in number 2 is that omega V is suddenly not anymore omega 1, but now the vortex-induced profile changes so that we exactly excites the second mode. And the reason for that is that the first mode is quite well damped by a so-called tuned mass damper, whereas in the second mode we will apply a pure viscous damper. So to be able to compare or to apply dimensioning of these two damper systems that we consider in this course, it's nice to have two different loading scenarios. One that is then taken care of by a TMD, and number two that is then damped by a pure viscous damper. In report number 2, we will only consider a multi-degree of freedom system. So the single degree of freedom approximation was a major part of report number 1, and in report number 2 we will only consider a full matrix equation. However, if you go back to the structure, we see that we originally have 26 nodes. So 26 nodes with 3 doves gives us the full 78 doves, and then we support, that is the two transverse displacements of node number 1, that gives us doves 1 and 2. Number 3 is the rotation of node number 1, that is free, that's therefore not supported, and then we again support doves 4 and 5. So these 4 degrees of freedom we then support, and that leaves us with the remaining degrees of freedom as being free. But in this case, in this report, we are going to apply system reduction. And we're going to apply system reduction in the form of a so-called master. Sorry, that's not a T. I was a little bit ahead of myself. It's a master-slave formulation, or a dynamic static condensation. And this is described in the course notes. More specifically, it is represented in section 4.5, and in particular it's 4.5.1 plus 4.5.2. So visit these two sections in the course notes, and basically all the math you need is available there. To make things a little bit easier, I decide on what is static and what is dynamic. And if we go back, then everything in the jacket structure we consider being static, while the doves associated with the tower are dynamic. So we make a split in the model. And that means all the static degrees of freedom are for the jacket structure, while the remaining upper degrees of freedom associated with the tower plus the RNA, the jacket is static, and these are dynamic. And that means, for instance, that the stiffness matrix is divided into 4 parts: purely dynamic, purely static, and the coupling between the static and the dynamic degrees of freedom. And the same split is simply made for the mass matrices. And then you have a look at the course notes, and that will provide you with expressions for the reduced size stiffness matrix and the reduced size mass matrix. And once you have these two, you can, by Rayleigh damping, create the damping matrix, and suddenly, whoopty, you will then have a reduced order system with only 33 degrees of freedom instead of the full 78 degrees of freedom. So in exercise 2.1, the first part of this report number 2, you're supposed to set up or determine these reduced order stiffness and mass matrices, solve the eigenvalue problem, and find the natural frequencies by this eigenvalue problem for these reduced order model, and of course compare maybe the first 5 frequencies with those we found for the full offshore wind turbine in report number 1. How accurate is this system reduction? Do we see a deviation on percentage? Are we down to per mils, or is it not even visible for the first 5 modes? So that is of course of interest, and the reason why we reduce to these limited number of degrees of freedom are of course for computational reasons. So we are going to make maybe fairly long time series analysis, and if we don't want to wait forever, it's nice to have a very compact model with only a few degrees of freedom, and static condensation, as done in this report, is one of the most effective tools to actually do this. So question B is then concerned with Rayleigh damping and find one alpha parameter and one beta parameter so that the damping ratio in the first two modes is equal to 1%. You can find the expressions exactly to be used for this solution in both the slides. No, not only in the slides, I think. They're not available in the notes. Then we again apply modal analysis, but this time we do it for the reduced order system. It doesn't really take that much of rewriting of the modal analysis code. A little bit in the beginning, defining the number of degrees of freedom. Try it out. It should work quite nicely. But of course, there's a little bit more programming with this part than I think you're used to in report number 1. And that's general for report number 2. Now I believe that you're more up to speed on the MATLAB programming. So let's try to be a little bit more ambitious from the programming side than we were for report number 1. So the idea is to plot the time history, of course, for the horizontal RNA when we apply the first mode excitation frequency, because when omega v is equal to omega 1, then we will excite mode number 1, and that will probably give us a vibration shape like this, forth and back, and that means that the top is probably also the max displacement, and that's why the RNA displacement, the u-top, is of most interest. When we then repeat this modal analysis, but now we excite for the second mode, then I think that the second mode was more like this. That means we'll have vibrations forth and back, and it's probably somewhere here in the middle region where we have Umax. Try it out, see which horizontal degree of freedom provides you with the largest deflection, and this type of deflection you can actually compare with the similar vortex-induced vibrations that we considered in report number 1. But be aware that omega v is now equal to omega 2, but this one is not necessarily exactly identical to the 9 radians per second from report 1. I think it is a little bit less. So therefore, do not expect the amplitudes to be exactly identical when you compare with report number 1. Let's have a look at the damper system part. Now, the introduction of this report is not considered to be a run-through of the theory for dampers and TMDs, not even for the time integration, but just to give you a brief indication of what you're supposed to do. So the idea is, if we go back, let's go for, here we are. So for the viscous damper system on the figure to the right, we simply add a viscous damper at node number 16. Now, this of course requires that we have a support right here. And in reality, this support is not there. But in principle, or the idea behind this, is that in practice, we are going to install a mass that is suspended by a hydraulic actuator. And this hydraulic actuator provides a damping force that exactly corresponds to the force provided by this viscous damper. And for the mass actuator, this is done by an active control law that is then modeled by this viscous damper system. So all the design of this control law is actually directly related to our ability to find C-opt, the optimal viscous parameter, and also to identify how much damping can we then introduce. But of course, this fictitious support is not there in reality. It's still some kind of reaction mass that drives the active actuator that provides a force on the structure that looks like the viscous damper that we have on figure A. Now, because the damper is located at node number 16, it is actually represented by a vector with a unit value in its first entry. And the reason why it's the first entry is that the degrees of freedom from 16 and above are those considered in the dynamic response. And that means in the dynamic system, the reduced order system, with only 33 degrees of freedom, in that case, node number 16 is actually node number 1. And therefore, we will have a unit entry at node number 1, actually at degree of freedom number 1, because the horizontal deflection of node number 1 is the first horizontal degree of freedom, and therefore our connectivity vector that describes the location of the damper on the structure is a 0 vector with only a single unit entry at its first position. And then we can simply add the contribution by the viscous damper to the original viscous matrix representing Rayleigh damping, and then we have our system of equations, now including the contribution of the viscous damper. Then a little bit on the theory behind the calibration of a viscous damper, and that is also considered in exercise 3.1. So this is actually the topic of next week's lecture. That means lecture number 9, which will also be online because university is still closed. So let's get back to that in next week's lecture. Then we will have the tuned mass damper, and the tuned mass damper would be the topic of lecture number 10. A tuned mass damper works differently than a viscous damper because a tuned mass damper can operate directly on the absolute displacement somewhere on the structure. It doesn't need support to provide forcing, simply because it directly contains this reaction mass, similar to what we have for the active mass damper over here, driven by the active control. But the tuned mass damper to the right in figure B is fully passive. And you choose M. I think M is 10 ton in the present case. And the question is then, what should K, the spring stiffness of the TMD, and C, the dashpot of the TMD, what should that be to get optimal damping performance? Again, we place the damper by a connectivity vector, and the horizontal deflection of the top node is then the third last entry in the connectivity vector. We can set up the forcing of the TMD. That's the viscous parameter times the deformation velocity. It's the stiffness times the deformation displacement. And this forcing works on the structure, but the vibration of the mass also depends on the forcing. So suddenly we have n plus, actually it's m plus 1 degree of freedom in our reduced system, because the last equation here is a TMD equation. So it becomes a little bit more complicated to analyze a tuned mass damper simply because it has its own dynamic equation. We put this equation 11 into matrix form, as shown here in 12. And that means that we're solving for this augmented or extended displacement vector, where the first 1 to m degrees of freedom are those of the structure, and m plus 1 is then the TMD. The matrices are given here, and those matrices you're supposed to implement in this exercise 3.2 that we have here at the bottom of this page. So that is definitely going to be an interesting thing to imply. Writing and talking at the same time is not a good idea. Implementing this is going to be a lot of fun. Now the calibration is not done for the full calibration, the tuning of K and C. This tuning is not performed on the full system. It's calibrated, it's tuned with respect to a dominating vibration mode. So this is only for resonance. So resonance, in this case, for omega 1. So that is, of course, our first loading case where omega V is equal to omega 1. So this is addressed by the TMD. We could have chosen mode number 2, but mode number 2 is taken care of by the viscous damper system, that with the active design. So the theory requires us to normalize the mode shapes. So this you also need to program in your code. Then you will, in the theory, find that you get two scalar functions. Once you go into the modal coordinates, two scalar functions that couple, and you have introduced modal mass, damping, and stiffness, and also the modal load. But once you have defined these quantities, you're actually ready to conduct the calibration. Because all the formulas in the course text actually are based on these entries here. So the first thing you need to do is that you need to find the mass ratio, which is the mass of your TMD divided by the modal mass. And remember that this modal mass is for a mode shape that is normalized to 1 at the TMD location. It's written in equation number 1, or 16, sorry, by this multiplication here. So this should be equal to 1. So that's the math behind it. This is actually the text, the underlying text that you might understand a little bit better. So first we're going to determine this mass ratio, because we know this is 10 ton. We have calculated this from 18a, so it's just determining mu. And then, once you know mu, there are actually formulas in course notes and slides for the natural frequency of the TMD and the damping ratio of the TMD. And these two you need to find, and once you have them, you can convert the KD, you can find that from omega d, and CD you can find from C to D. And that you're supposed to do in B. And once you've found KD and CD, you are actually ready to implement that in your system. However, there's also an expression given for the additional damping that the TMD is supposed to provide. So have a look at the theory and find an expression for this modal damping that the TMD provides. And once we do the simulations, it might be interesting. Do we get this? The final part is then concerned with time integration. And time integration means finding response histories. That could be at resonance, could be something like this, as function of time. So find this, and we are going to apply a so-called Newmark method. So it's an alternative to modal analysis. And the idea is that modal analysis we cannot use because our dynamic equation contains a term like this. And a term like this violates the orthogonality condition. That is the basis of modal analysis. And that's the reason why we need to go into direct time integration of the equation of motion. Let's have a look at the two equations of motion that you're going to solve. For the TMD, we have this one, so you're going to solve this one by Newmark for TMD structure. And let's go back. And this one, you're going to solve by the Newmark method for the case with the viscous damper. And the exercises, the questions in 4.1, of course, address this. So in the first question, we're going to look at the viscous damping case. And the viscous damper was for mode number 2. So in this case, the loading should be for omega v equal to the mode 2 natural frequency. So that we are sure we are at the worst case, we design to the worst case, that is resonance. We know that. So find QD by the Newmark method and plot a time history like the one we did for the modal analysis in question 2.1d. Try to compare the steady state amplitude with the damper to the case without the damper that we considered previously. How much extra damping do you get? And can you determine that by comparing the damped response with the undamped response? The answer is yes, but the question is, does it really match the zeta max that you found previously with the tuning theory? Then we go and switch to the TMD analysis. So again, run the Newmark procedure for the TMD equations. In this case, plot the RNA time history, find maximum displacement, and compare again to the case without the TMD in exercise 2.1c. Then you could also, in this case, plot the time history of the TMD displacement, because this one is contained as m plus 1, the degree of freedom m plus 1 at the bottom of our here of our solution vector. So UD is given as the bottom row in Q, and this one you can as well plot. And from theory, you will find that this one is much larger than the Q RNA. So the drawback of using a TMD is that the TMD mass has a much larger amplitude than the structural response. So you need to be careful that you have space enough inside your structure, inside your nacelle, inside your tower, wherever you're going to apply this, inside your bridge, for these very large deflections of this TMD mass. The final question then concerns an alternative Newmark method. That's the so-called Fox-Goodwin method. And this Fox-Goodwin method is actually not unconditionally stable. It has a condition for stability. So try to find the conditional time increment and see if you directly apply this time increment. Will you get stability or instability? What if you take a time increment that is a little bit larger than the stability limit? Then you should see stability, but how much larger should it be? The question is, how accurate is this particular limit that we're going to derive in lecture number 11 for the Newmark method. A little bit on the report instructions, 15 pages compared to the 20 pages for report number 1. Be careful how much you show, derive. Be very conservative with how you set things up so that you stay within these 15 pages. Remember to have important theory and also to discuss results. But we will also have some nice figures, curves, plots, and all the rest I can't remember right now. So enjoy, and let's have a talk on Piazza during report number 2 with your questions. Do not hesitate to write. I think it's important to write on Piazza because then everybody else will also see your comments, and in this time we should help each other. So enjoy.